Chapter 4 is on estimation techniques. You may recall from talking about stuff from Chapter 2 and Chapter 3 where we had these equations that we were playing around with, either supply and demand equations or equations with marginal benefit and marginal cost, and we solve those things to answer questions about the particular markets. But you may have wondered, where did those equations come from? And what I presume happens with most businesses is you don't just sit down someday and someone plops some equations in your lap and says, please solve these. Usually, I imagine what happens is you might have a few points of data. You might have a few price, quantity combinations, and what you would like is to be able to get some equations out of that. So what we're going to do in Chapter 4 is to figure out how we can take bits of data, pieces of data, maybe a small Excel table, and turn those into equations that we can interpret according to our theory that we've developed before. So again, we're going to end up with an equation, but we want to kind of discuss the terminology that we're going to use from here on out. So we'll talk about parameters first. When we had the demand equation before, we had the quantity that was demanded was based on the price of the product and income and prices of substitutes and lots of other things. Well, we recognized that the quantity depended on the price, but we want to be able to quantify that somehow, to be able to say, well, if the price increases a certain amount, then how much does that cause the quantity demand to change? And we can quantify that using these parameters, or a coefficient, in an equation. So a simple equation for the slope of a line, y equals a plus b times x. We might have data for the y variable, maybe the quantity demanded, and the x variable, the price. But what we don't have are the a and the b. I don't know how much people would be willing to buy regardless of the price, which is going to be what the a coefficient tells us. And I don't really know the relationship between price and quantity demanded, how responsive consumers are to a change in the price, which is what the b coefficient is going to tell us. So I'm given y and x, and I want to find a and b. Once I know the values for a and b, then I can use that equation to think about some hypothetical values for price, or x, and be able to make a prediction about the expected value of y. So there's some examples of a coefficient estimate, the a being 4 in the first equation and 0.4 in the second, the slope parameter, the b parameter, being 2 out front of the x in the first equation, and negative 3.7 in that second equation. So what we want to be able to do is to estimate the values of these parameters using the data on y and x, and run it through some mathematical algorithms to come up with estimated values of the a and the b parameters. And there are different ways different phrases that's used for this, either estimation, or running a regression, or doing ordinary least squares, OLS, lots of different phrases, but it all means the same thing. We're taking data on the variables that we have, the y and the x, and we're using that to come up with estimates of the values for the a and the b parameters. So like I said, the most common way of estimating parameters is by using regression analysis. This is a statistical mathematical technique for getting the values of those parameters, and not only that, but figuring out how confident you should be in the results of that analysis, results of those algorithms. Again, you're inputting data on y's and your x variables, and the computer package is going to spit out values of the coefficients no matter what. But that doesn't mean that in one instance the regression coefficients have been estimated well. It doesn't mean that they're always estimated well. There are going to be ways that we can test how confident we can be in the results that we're getting. And that's going to be an important step, because again, the computer just is going to give you an answer no matter what. And you don't just want to run with the answer if you dug a little bit deeper and found that you shouldn't really have a whole lot of confidence in the results that you've been given. And basically what regression analysis does, if you can think of just a simple two-dimensional plane, you have a y-axis and an x-axis, and think about data being scattered throughout that plane, then what regression is going to try to do is to find a best fitting line that goes through those points. It's not going to probably go through each point exactly, but it's going to try to figure out what is the best fitting line, what line goes through those points the best, and it comes out with the values for the a and the b based on that. And if you can kind of conceptualize that in a two-dimensional space, then that would be if you have a y variable and only one x variable. The same sort of thing is true if you have more than one x variable. Like with our demand equation, we had the quantity demanded depended not just on the price, but it depended on income and prices of substitutes and all those other things too. We'll start just by talking about what's called a simple linear regression. The only reason they call it simple is because you have one dependent variable and one independent variable, one y and only one x. And you can get into, like I said, with the demand equation where there's more than one x variable, like price and income and prices of substitutes, and they call that a multiple linear regression. So it's not, the methodology is exactly the same. They only call it simple because of the number of variables that you're treating. But again, we're only going to think about a y variable depending on an x variable, but there's also this intercept term, this a, and there's a slope parameter, or the b term. You can think of the a value as if the value of y is, if the value of x is 0, then is there still going to be a value of y? And the intercept may actually be 0. But you might think of the idea that if we're thinking about demand, then people may demand a certain amount of a product regardless of what the price is. So if it's food, then you can think, well, people are probably going to buy food even if there really isn't much of a price to talk about. So the intercept, the a parameter there, kind of gives you that idea. The slope parameters are going to probably be what's more interesting to us, because when we're doing these things, we want to figure out, well, if the price changes by a certain amount, what effect does that have on the quantity demand? So if my x increases by 1 unit, what change does that impose on the value of y? And that's what the b value, the b parameter, is going to tell you. It tells you if x were to increase by 1 unit, then the change in y will be the value of b. The way that regressions try to figure out what's the best equation, what are the best values of a and b to give back to you, is by minimizing the sum of the squared residuals. And so you can think of the computer as trying to come up with all different values of a and b, all different values of intercepts and slopes, so it's going to plot these lines all over the place. Some are going to be, positively sloped and steep. Some of them are going to be positively sloped but flatter. They might even consider a horizontal line. Some of them might be negatively sloped and steep, etc. All different variations on a and b that you could conceive of. But it's trying to find the best line, the line that fits through the data the best. And the way that it determines this is by figuring out, well, what is the actual value of y that was inputted, and then what would be the estimated or the fitted value of y that would result if the a and the b that we're currently considering, the line that I'm currently considering, what would that estimated value be? And figuring out the difference between those two is what they call the residual, or sort of, you can think of it as how badly the fitted value is compared to the actual. So if the residual is large, then that means that the estimated value of y is quite a bit away from what the actual value of y was. We square these things because sometimes the the estimated value of y might be above what the actual value was, and so the residual might be some negative or positive amount. But then it might go the other way too. The actual value might be below the fitted value. I may have confused my wording there, but hopefully you can understand what I'm talking about. And so you square those things because it gets rid of the negative sign. You might have some positive residuals at one point for some data points, and you may have some negative residuals for the other data point. You don't want those to cancel each other out. So when you square them, it gets rid of the negative sign. Adding all of those up kind of gives you the sum total of the error, or how badly the actual and fitted values are. And so we have this sum of the squared residuals to kind of give you a sense of, again, how badly that particular line you're considering fits the data. And of course you want to choose the line that has the smallest of those sum of squared residuals. You want to pick the line that minimizes the sum of those squared residuals. So we call that, I don't know where the word ordinary came from, but we call those ordinary least squares. So again, you have this squares part of it, meaning the squared residuals that you're adding up, and then the least saying that you want the minimum of those sum of squared residuals. And again, this will give you the value of the best fitting line. So here's just an example of how data might be scattered around a graph, and you wanted to get this best fitting line. You can kind of eyeball it and see that the relationship between advertising expenditures and sales seems to be positive. And again, a reason we might be analyzing this is we want to know, well, maybe there's a certain amount of advertising that we're considering doing. Can we come up with a prediction about how many sales should result from that? And again, being able to use this data to come up with an equation will be very helpful, because once I have an equation, I can just plug in the amount of advertising expenditures we're considering, and we'll get out an estimated value of sales. It's not going to be perfect probably, but it'll be hopefully a pretty good estimation, pretty good approximation. So given the data that's here, and you might actually be able to find the data used here, maybe in your book, the estimated line that the computer came up with was the red line that's drawn here. Again, you may consider other possible lines, a line that might be somewhat flatter or somewhat steeper, maybe even one that's downward sloping or negatively sloped. But the computer determined that this was the best. This was the line that fit the best. And it sits where the red line is sitting, and that results in an intercept of 11,573, and you can see that hitting the sales axis, right at 11,573, and it has this slope of 4.97. Again, how it determined that is by thinking about the estimated value. So if we plugged in 7,000 as the value for A in that sample regression line equation, so 11,573 plus 4.9719 times $7,000, then the estimated value of sales that comes out of that equation is 46,376. You can see that that's quite a bit away actually from the actual data point, the actual amount of sales that happened, which was $60,000 of sales. So there's this error, there's this residual between the actual data point of 60,000 and the estimated or the fitted value of 46,000. So again, the way that the regression is coming up with this best line is it's calculating this residual for each of the data points that's here. It's figuring out this residual for each of those little black dots, the distance between the black dot and the red line, and it's trying to come up with which line minimizes the sum of those distances, the sum of those errors. And it determined that the best line that does that minimizes those, is the line that was given here. It might seem like that E1 residual or error seems kind of large, but you could, if you think about other lines you could plot, the total residuals of all of the points would have been much greater than the one that's given here. The reason we do this is because we presume there is this underlying fundamental relationship between the x variable and the y variable. The only way we can uncover that relationship, though, is by using actual real-world data, which can be kind of messy sometimes. So the estimates that we get, this a hat and b hat, the estimated coefficients usually aren't going to be exactly equal to the true fundamental underlying relationship between the x and the y variable. So the estimated parameters that we get aren't going to be exactly equal to the true values of those parameters, because again, we're using, it says random there, it's not exactly random, but we're using data that we've obtained from someplace else to estimate the values of these things. What helps is, and again, we can't be guaranteed that the estimates we get are going to actually be related to the real true underlying parameter estates or parameters themselves. So what helps, though, is being able to get more data. You can imagine in the previous picture, if we only had 2 data points, then actually you'd be able to fit a line exactly, because all you'd have to do is draw a line connecting those 2 points, and you could say, hey, there's this relationship between the amount of advertising and the amount of sales, and you might say, hey, that fits these 2 data points exactly. There's no residual here at all. This is the best line we can do. But you might also say, well, yeah, but that's only 2 data points. You just have 1 year's advertising and sales numbers, and then another year's advertising and sales numbers, and you can't really generalize that every single year the advertising sales relationship is going to be exactly the same. So what certainly helps is being able to obtain more data so that you can fit lines through more pieces of information. And the more you do that, the better confidence you can have that the estimated parameters, the parameter estimates, are closer to the true values, the true underlying fundamental values of A and B. You may have heard the phrase when people are talking about particular scientific studies that they'll say one variable is statistically significant in relationship to another, or there was a statistically positive effect of one variable on another. And they're talking about this idea of statistical significance. The idea is that we're trying to uncover the quantitative relationship between an x variable and a y. And I know that I'm giving Excel, or I'm giving the computer some data, and it's always going to spit out an estimated value of b for me. That value might be large, might be small, but it's going to give me something. And it's very rare that it's going to give me a value that's exactly 0. But there may be times when you sort of think theoretically, or you might even not know this, but there may be times when the real true relationship between x and y is 0. There's no relationship at all between these 2 variables. When we talked about a demand equation, we had, for our x's, we talked about the price and the income of consumers and the prices of substitutes. You may think about including another variable in that equation and say, well, I think the demand for this product depends on the amount of rain that fell that day. So you have not only data on price and income and price of substitutes, but you have the inches of rainfall on that particular day. And theoretically, you might think that doesn't seem to have any relationship at all. Or you might not even know. Maybe it's car sales, and maybe rain does have an effect. But if it's something else like lettuce, then people buy at a grocery store. There probably isn't a heck of a lot of relationship there. But we want to know, because Excel is going to give us a value of b that might not be 0. So again, there's this question of, well, should I have faith in this estimate that I've been given? Excel is going to give me an estimated value of b, this b hat, but it may be that the true relationship between x and y is 0. There's no relationship at all. If I just run with the fact that Excel has given me an estimated b hat that is not 0, then I might conclude that, oh yeah, rain is really important in determining the demand for lettuce. It might also go the other way, where the real world impact of x on y is significant, is important, but the estimate that you get from Excel is close to 0. And you might just say, well, I don't think that x is important because its estimated coefficient was so small so that x variable doesn't matter at all in terms of y. You might dismiss it out of hand, when in reality there is an important effect, even though it might be somewhat small. This will matter a lot based on the scales of the values that you're using for your y's and your x's. You might think about y being the demand for houses and x being one of the x variables being the price of houses. And so if you run a regression with the number of home sales as your y and the price in dollars of the house, well, the estimate of b is going to be, if you increase the price of a house $1, what happens to the amount of sales of that house? And it might be negative, but it might be extremely small. I mean, the increasing the price of a house by $1, I can't imagine that's going to have a huge effect on the number of homes that are demanded. So you might actually get an estimate for that b that is very, very small, very close to 0. And you might say, well, that shows that there's no relationship here between these two variables, the price of the house and the amount of sales. But of course, theoretically, that's a huge, they're hugely significant, hugely related, the price of a house and the amount of sales. So even though the estimated value of b might be really, really small, you sort of know intuitively that this is important. The true relationship is not 0. So again, it kind of cuts both ways, and we have to come up with a measure of this statistical significance. There are different tests that we'll use for this, and they're going to fall into this t statistic and p values. And actually, these, even though there are two tests here, they're actually related. There's always this chance that the actual relationship between x and y is 0, even though the parameter estimate may not be 0. So we want to come up with this level of significance, figuring out what's the actual probability that the parameter estimate that we have shows up as being 0 when in fact the underlying relationship actually is 0. So this level of significance will give you a sense of how much chance is there that the true relationship is 0, even though the parameter estimate that I'm looking at is not. And so you hear people talk about a level of confidence that they'll have in the estimates. So if people say that this variable is statistically significant at the 10% level, then that means that there's a 10% chance that the true relationship between x and y is 0, meaning there's no relationship between x and y. There's a 10% chance that could happen, even though the parameter estimate is not 0. And so on the flip side, what that means that if you have a 10% confidence level, then that means that, again, there's a 10% chance the true relationship could be 0, but you have a 90% chance that it's not. So if a variable is statistically significant at the 10% level, then you can have 90% assurance that the parameter estimate is correct and that there is a relationship between x and y. Again, only a 10% chance that it's not. Only a 10% chance that even though you see a non-zero coefficient estimate, that the true relationship is 0. So you have 90% confidence that what you've estimated is actually correct. Each variable that you're estimating is going to come with a t statistic. The computer is going to calculate a t statistic for you. And again, this will help you to determine how significant that estimate is for the underlying relationship between these two variables, the x and the y. The t statistic is a ratio of the estimate of b relative to its standard error. So probably an easy way to think of this, if you're not up on all the stats part of it, is if you think about a group of people in a room, you can figure out what the average height is of the people in the room, and that's kind of like the estimated b here. But obviously there's going to be people who are a little bit taller than the average and people who are a lot taller than the average, some people who are a little bit shorter than the average, a lot shorter than the average. So you're going to have this dispersion of data around that mean. So you're going to have a mean value, this B, but you're also going to have this sense of how dispersed the data is around it. And that's going to be reflected in that standard error. If you have a lot of people who are at the really tall end to really short end, your data is probably very dispersed. It's very kind of widely dispersed around that estimated B, or around the average. In that case, your standard error would be fairly large. If all the people in the room are maybe within 1 or 2 inches of that average, so they're all basically the same height, and then the average, the B hat there, is going to be a pretty good reflection of the average height of the people in the room. So in that case, the standard error would be relatively small. There wouldn't be a lot of dispersion around the mean. So thinking that way, the t-statistic then, if the data is very tightly packed, like if people are basically all the same height, then that standard error is going to be very small, and that's going to make the t-statistic relatively large. On the other end, if you have a lot of tall people and a lot of short people, so the data is widely dispersed, then your standard error is going to be large, and that's going to make your t-statistic relatively small. So again, it tells you, given this single point estimate, how widely dispersed the data is around it, and whether the t-stat is small or big gives you a sense of how confident you should be in that estimated value of B. We have our estimate of B hat. We have our t-statistic telling us how dispersed the data is around it and how much confidence we might be able to have in that. But we want to have this criteria for figuring out, again, whether we should consider this variable to be significant or not. We want to perform what we call this t-test. And basically we say, okay, given the t-statistic that I have, then I need to compare that to kind of a standard level of t that tells me, again, the probability that this estimate is equal to 0. And usually the cutoff we use is a t-ratio of about 2. So if you get a t-statistic that is greater than 2, then again, that means that the standard error is relatively small. The dispersion of the data is relatively small. So that means that you should have a lot of confidence that the estimated value of B hat that you have is consistent with its true relationship, that it was estimated well. If you get a t-statistic that is less than 2 or less than 1.96, then that's an indicator that the variable is not significant, that even though you're getting an estimate that's not 0, even though you're getting a B hat that is not 0, the true underlying reality of the relationship between x and y is actually 0. X and y don't really have any relationship to each other. The t-statistic can be a little strange. I mean, you're trying to keep in mind this thing about, well, is it greater or less than 2? And it's by itself, it might not be very intuitive of what it's supposed to mean. And so we also use these, what we call p-values, probability values, and these, for me, tend to make a lot more sense. When I see them, then it makes more sense to me to interpret it. All the p-value does is take the information from the t-statistic and sort of transform it into a probability. So if you find out that your t-statistic is high, then again, that means that relative to its estimate, its standard error is very low, the data is tightly packed around that average, and so you can have a lot of confidence in it. So what the p-value tells you is basically the probability that the variable is insignificant, the probability that the real underlying coefficient value should be 0. And so for a variable that is highly significant, that has a high t-statistic, you would expect that probability of being 0 to be very low. If the p-value is low, again, that means that there's a very low chance that the actual coefficient value is 0, which means there's a very high chance that your variable is significant, that there is a relationship between the x's and the y's. Think of this as a probability, then your p-values are always going to be between 0 and 1. And if you're hoping that your variable is significant, then you want to aim for a t-statistic that is high, which also means you're going to look for a p-value that is low. The lower p-value means your variable is more significant. A higher p-value means that it's less significant. So sometimes you'll hear people say, well, this variable is statistically significant at the 5% level. That means that its p-value is less than 0.05. Now you've figured out your t-statistics and your p-values, so you can have a sense of how accurately the individual variables have been estimated, how much confidence you should have in those individual values of b for each of your x variables. There's a different kind of idea about, well, how much confidence should I have in the entire set of variables that I picked? So it's one question to say, does price have a relationship to the quantity demanded? It's another question to say, well, I think that the things that matter for quantity demand are price and income and the price of substitutes and the size of shoes of the consumers. So 4 variables there, one of them's a little odd. So you'd probably find that the t-statistics, or the p-values, would show the first 3 to be significant, but the last variable to be insignificant. So again, that's a sense of what the t-statistics tell you, or the estimated coefficients for the individual variables. But again, it's a different kind of question to say, how good do those 4 variables do at explaining the variation that I see in quantity demand? Did I do a good job picking these 4 variables all together? So again, it's kind of a different issue when you're thinking about the value of the variables you've chosen versus the individual estimates of the coefficients. So to get a sense of the accuracy, or how well the model or the number of variables that you picked are behaving, there's this coefficient of determination, or this R squared. And it's kind of a probability, I guess, more like a percentage. It'll tell you the percentage of the variation that your dependent variable is showing that is explained by the independent variables that you've picked, by the regression equation that you've picked. So this is going to range from 0 to 1 because, it's a percentage. You have this set of x variables that are trying to explain variation in the y variable. So if you've done a good job, if you've picked x variables that do a very good job of explaining how your y is behaving, then you're going to get an R squared that's relatively high. So if you've picked price and income and prices of substitutes and complements, then those 3 or 4 variables may do a good job in explaining the amount of quantity demand that you're seeing. And you might get an R squared that's maybe 0.6, 60%, 70%, meaning that those 4 variables you picked are explaining 70% of the variation in your y variable. And that means that there's 30% left over that is unexplained. But again, since we're dealing with humans, and humans can behave sometimes erratically or randomly, then that's always going to happen. But anyway, getting a higher R squared means that the variables you've picked are doing a better job of explaining variation in your y variable. So looking at the R squared is good. There's another statistic that you'll see show up in regression results called the adjusted R squared, or sometimes it'll be an R bar square with a little bar over the top of the R, kind of like an underline, but on the top instead, an overline, I guess. One of the features, just the mathematical realities of the R squared concept is that if you include more x variables, even some that may be completely irrelevant, if you include more x variables, the R squared is never going to fall. So we try to interpret this R squared as telling me, how good of a job did I do in picking independent variables to explain my y variable. Theoretically, if I include an x variable that's irrelevant, that makes no sense, like the shoe size of my consumers, then that would suggest that the quality of my model, the quality of the variables that I've chosen has gone down somewhat, because I've included this weird shoe size variable that doesn't make any sense. And you would think that, well, that should be associated with a reduction in the R squared, but it doesn't do that. Just mathematically, the R squared is never going to fall when you include more variables. And so to correct for that, to correct for the inclusion of independent variables that are kind of irrelevant, there's this adjusted R squared. So usually whenever if I have just one x variable, if I have like a simple linear regression, then I might look at the R squared just by itself and say, okay, that's doing a good job. If I have a bunch of x variables though, if I have not only the price, but also income, prices of substitutes, then I usually look at the R squared instead, because again, that kind of corrects for the fact that there's these multiple numbers of independent variables. Oh, the F-test. It's another kind of statistic, sort of similar to the R squared. It tries to capture the same sense of how well do the variables you picked do in explaining variation in your y variable. You can kind of think of it as when you had a t-statistic, that was for one single variable, whether that single variable is significant. The F-test kind of is a similar thing for your entire set of independent variables. So if the F-test shows up statistically significant, then you go, okay, the variables I picked were good. I tend to not look at this too much because almost all the time the variables that you've picked are going to do a decent enough job at explaining variation in your y variable. So it's very rare that your F-test shows up as insignificant. If it does, of course, then you really need to rethink the variables that you've picked. But most of the time it shows up as significant, and it's just kind of like, okay, so I'm just going to kind of move on. So we talked about having a single regression model where you have one independent variable. But a lot more interesting is to include more variables than just one. So I don't just care about how price is related to quantity demanded, but how price and income and prices of substitutes are related to quantity demanded. And in that case, I want to do a multiple regression, or I want to have multiple independent explanatory variables. When you do this, again, you're going to get an estimated value of b for each of your variables. You're going to have a coefficient for your price, and a coefficient for income, and a coefficient for the prices of substitutes. And again, you'll get a t-statistic for each of those, figuring out whether those variables have been estimated with a certain degree of statistical significance. The way you interpret the individual coefficients, the individual b's, the b for the price, the c for the income, the d for the price of substitutes, the way you interpret that is to think of it as this is the effect that price has on quantity demanded, holding the values of all of the other variables constant. So if I'm going to figure out, well, what's the relationship between price and quantity demand, if I have these other variables in there, like income and price of substitutes, then the coefficient on price tells me if I hold income and prices of substitutes constant, then the relationship between price and quantity demanded is equal to b. If I'm interested in how income relates to quantity demanded, then the c coefficient on income tells me what the effect of income is on quantity demanded, holding price, own price, and the price of substitutes and complements constant. So it's kind of like it's sort of like a derivative where you have this marginal effect of one independent variable on the dependent variable, holding the other independent variables constant. There are a few special categories of multiple regression models that are going to be useful for us. One of them is going to be the quadratic regression models, and this is going to be helpful when you have data that is curved. When we looked at a demand curve, well, a demand curve was, even though we called it a curve, they look like straight lines. Sometimes they're not straight, but just kind of the textbook example that we have. Your demand curve slopes down, it's a straight line, and you can show that there's a linear relationship between the price and the quantity demanded. When we looked at the total revenue curve, though, you saw that it had this hill shape. It was curved. The total benefit curve that we did in chapter 3 was curved. The total cost function had some curvature to it. So these were not straight lines, but you can sort of modify the data that you're looking at to transform a linear regression model into accounting for the curvature of these particular shapes. And you do that by including not just an x variable, but you also square that x variable. And just by doing that, it tends to, it fits the data well. And we'll see some examples of this a little bit later on. If you're going to estimate this kind of a regression, where you have the total revenue as your y and the quantity as your x. Again, if I were just to give you some data on quantity and total revenues in Excel, you had one column of Q's and another column of total revenue. If you plotted that, then again, you'd see this hill shape. What you can also do to transform that, to be able to estimate it with a regression, is to make not just a Q column, but a Q squared column. And that's like your column Z, I guess, because you're calling it this new variable Z, equal to x squared. And then when you run your regression, you say, well, I want to have total revenue as my dependent variable, my y, and I want to include x, the quantity, as one of my independent variables, and I also want to include this z, or this q squared variable, as a second independent variable. Doing that will allow you to estimate an equation that at the end of the day is going to allow for this curvature of the total revenue curve. Quadratics are for equations that are U-shaped, that have a hill or maybe kind of a valley shape to it. If you remember back to your principles micro, you may recall looking at a marginal cost curve or the average cost curves. Those are U-shaped things, so those can be fitted with quadratic regressions. The total cost line had kind of an S shape to it, so it's kind of a combination of two curves, and one of the curves that again, a total cost curve had that. And a way that you can model that with two curve changes in it is by a cubic regression model, which includes not only an x and an x squared, but also an x cubed term, so hence the cubic. So we use this to fit data that has these two directional changes to it. And again, here you're going to make another column that is your x squared term, and you're going to make another column, this w, that is your x to the third power column. And then when you run a regression, you say, well, I want my total cost, my y, to be a function of q squared, and q to the third power, q cubed. Some other variations that we won't really use too much in this class. Log functions. Actually, we probably won't use this in this class. I actually do it in my consulting when I'm trying to estimate the value of a yield curve. If you have a sense of what a yield curve looks like, you get relatively low returns at short maturity lengths, and as you move out to 20, 30-year maturities, the yield increases. And so when I'm trying to do my consulting and estimate this yield curve, I tend to use linear regression models, but we won't really use it too much in this class. So what steps are you going to undertake when you want to run a regression? First thing, the most important, I think, is specifying the equation, figuring out what exactly do I think is important in determining the values of this dependent variable. So you need to pick the x variables that you want to include. Now, you may be tempted to just kind of take a kitchen sink approach and just pick every single variable that you could possibly think of that might affect the particular dependent variable that you're considering. What should drive your choice, though, is economic theory. What do you think is theoretically important? So if I'm thinking about the demand for a product, then again, theoretically, I recognize that the price of the product is important, the income of consumers is important, the price of substitutes and complements is important. There's always this temptation, though, to throw other variables in that make the result look better. And so, well, I ran this regression with these variables that I think are theoretically important, and I got an R squared that was, around 0.5 or so, and that's 50%. I got some t-statistics that look okay. Let me throw in this shoe size variable. And you may find out, just by pure random chance, that including shoe size as one of your x variables makes the R squared go up, or even the adjusted R squared go up. And you go, oh man, that was great. This is a wonderful model now that I've got my shoe size variable in there. Well, theoretically, you would think there's absolutely no relationship there. So you don't want to pick variables because it makes your results look better. That's not what your goal is. Your goal is to have theory inform the variables that you pick. So if we're thinking about the demand for pizza in a college town, then we might specify an equation like this. It looks kind of messy, but demand for pizza, the quantity demanded of pizza, is my y. And I know I've got to have my intercept term in there, the a, and then I have these other variables, the price per slice of pizza, my x1, and that'll be associated with a coefficient of b1. I think the income is supposed to be important, but you might not be able to get the actual income of students living in this town. So you might say, well, kind of a proxy for that, or a close approximation of income, is to look at the annual tuition of this college. Because you might think that for colleges that have a higher tuition, the students who attend that school probably have higher income, or they come from higher income families. You can't measure income exactly, but you can measure this tuition, and that might be a good proxy for income. So that'll be my x2, and it'll have a coefficient of b2. I think about substitutes and complements, and here I've got a complementary good, the price of a can of Coke, as my x3 variable associated with a coefficient of b3. And you might also think, depending on where the campus is, there might not be a lot of other options for the students to pick other restaurants. And so you might say, well, I'm going to have a location variable where I'm going to, we call x4 a dummy variable because it only takes on two values, a value of 1 or a value of 0. I mean, the price per slice, x1, that's going to take on all sorts of different numbers. I mean, you could have $1 a slice, or $1.20 a slice, or 97 cents per slice. So the x1, the x2, and the x3 are all going to take on, numbers that could be all over the place. But the x4, it's restricted to only being a 1 or a 0. We call that a dummy variable. And we're going to define that to be, if the campus is in an urban area, then I'm going to record the value of x4 to be 1. If the campus is in a rural area, or not in an urban area, then I'm going to record a value of 0 for that x4 variable. That'll have this coefficient of b4. And then you see the u at the end there. That's kind of an error term. It's supposed to catch the effects of all the other variables that you haven't included. So interpreting that may be a bit beyond this course. Once you've decided which variables you're going to include, you want to specify the equation, meaning you want to sort of transform those variables you think are important into an equation that you can actually run a regression on. I guess one of the important things I should have mentioned before in picking the variables that you want is you need variables that are quantifiable. So you might think that, well, the demand for pizza in a college town might depend on the school spirit of the students, because they get more excited about home football games, and if there's more school spirit, then there's more tailgating and ordering pizzas to watch the games. Well, that might be true, and students who behave that way might order more pizzas, but I don't exactly know how you would quantify the level of school spirit of a particular college town. What is it? How would you get numbers for that? So the variables that you include all have to be, have to have numbers associated with them. You have to be able to quantify the variables that you're talking about. So when you specify the equation, again, you're sort of transforming these variables into an equation that you can actually run a regression on. A way of doing this might be if you think that, I think that the total revenue depends on the quantity, and so you think that's an important variable, but you'd also want to, in terms of specifying the equation, in terms of getting it in an equation form that you can run a regression on, you would say, well, total revenue depends not just on Q, but since it's hill-shaped, it's going to depend on Q squared also. So when I specify my equation, I want to have not only a Q independent variable, but also a Q squared independent variable. So anyway, back to our college town. Here's our little equation that we're going to estimate. Again, each of the B's that are here will be the coefficients that the computer is going to give us a value of. It's going to estimate the value for. Also for the intercept term there, the A. And so they'll be the coefficients, or the slope, if you want to think of it, slope parameters. And again, they're going to represent the influence of each individual x variable on y, holding the other x variables constant. So B1, the way I interpret that is to say, well, if x1 increases by 1 unit, then it's going to have this effect on y of the magnitude B1, assuming that all of the other x's are being held constant, assuming that x2, x3, and x4 are being held constant. So we can kind of think of it, each individual b coefficient there, b1, b2, they're all basically partial derivatives, if you know what that means from calculus. The a is an intercept term, and we mentioned what that means before. Again, the u is kind of this error term that's supposed to kind of capture the influence of all of the other factors that we haven't included. Obviously the demand for pizza in a college town is going to depend on more than just the 4 variables that we included here. But it's pretty much impossible to include every single influence that could possibly affect the demand for pizza in a college town. And so, since it's impossible to obtain all of those important variables, then we know there's going to be this certain degree of error, a certain amount of variation in y that we're not able to explain. And so you have this error term in there. And again, this might be of more importance if you are more interested in statistics. You're going to think that I make a big deal about certain aspects of running regressions, but I think they're important. One of the important things is to pick the variables that are theoretically important. You don't just want to include variables that are going to make your results look better. Another thing that I think is critically important is to come up with hypotheses. So I've picked my variables, my x and my y, and I want to come up with a guess, or come up with a hypothesis about what effect do I think there will be. Do I think the relationship between x and y is a positive one or a negative one? If it's a regular type of product, then I want to come up with a guess. B1 was the price coefficient. Do you think that the relationship between price and quantity demanded is positive or negative? Well, I think it's negative. Do you think the relationship between income, the B2, income and quantity demanded is positive or negative? Well, I think that that's positive. You have to have a guess beforehand, before you see the results, because you need to know if those results make any sense. If you don't have any idea beforehand what you expect to see, then you might just see some results and you just run with it. And you say, hey, these are the results that I got, and I'm just going to go with these. And you wouldn't really have any clue whether the results that are in front of you are making any sense. It could just all be garbage. It could just be some random way the data is constructed, or the sample that you picked. You get some results that in reality make no sense at all. But if you haven't thought about what the effect should be, then you don't really have a sense of how important you should consider these results to be. So again, you want intuition and again theory to inform how you interpret these results. Just because you get good results, that doesn't mean that the relationship between these variables is going to hold all the time. So again, the results might be just a statistical artifact of some weird data that you picked that time to sample from. So you want your intuition to guide you as to how well the results are, how good the results are. You shouldn't use your results as a guide to your intuition. You might find that after you run a regression, hey, the shoe size of the consumers really mattered in deciding pizza demand. So really, we should try to locate in towns with people that have big feet. Well, again, in that case, you'd be using your results of a significant coefficient on your shoe size variable to guide your intuition, and that would just be ridiculous. Use theory to figure out the variables you want to include. Use theory to come up with some hypotheses so that you can interpret your results. what you should be spending most of your time on is thinking about the variables you want to include, thinking about the direction of the effects, thinking about the relationship between your x's and your y's. What you probably will be spending a lot of time on, unfortunately, is actually getting the data. And I mentioned that you want to use variables that you can actually quantify. So I don't know how you would code or what numbers you would use to measure the mood of a town or the school spirit of a town. So you want to use variables that actually are quantifiable. When we talked about the demand for pizza, you might have thought back to chapter 2 and said, well, that should depend on the price, and you said income. Income should have been important, but you didn't have income in the equation that you specified. You just used college tuition in that town. Well, unless you work at the IRS, you probably don't have access to income information of individuals. So a way you can do that is to say, well, I can't get income exactly, but I can get something that's kind of close. I can get a decent enough substitute for an income variable. And we call those proxies, where you say, well, I'm trying to get income, but I can't get it, and so I'm going to use this sort of substitute variable, this tuition variable, as a proxy for income. And again, we use that because, well, I can get data on the tuition of the town, and it's kind of probably closely related to the income of the students. If the tuition is high, the incomes of the students or their families are probably high also. So you can use proxies if you need to. That's perfectly fine. You may have also said, well, we had this other variable about the location of the town, whether it was urban or rural or not urban. And we said, well, it's kind of hard to quantify that too, the location of a campus. And you might have thought that the location matters because if you're in an urban area, there's probably a lot of other options for people to eat instead of just pizza. There's probably Thai food places and lots of other places you could eat besides a pizza place. Whereas if you're not in an urban area, there may not be as many. You might have a few pizza places and not many other choices. So we think that that's important. And you might have quantified that by saying, well, I'm going to get the number of non-pizza type restaurants in this town. That might be a little difficult to quantify also, or a little difficult data to collect. So we said, well, you could sort of use another kind of substitute, another sort of proxy, is just to say, well, is this campus in a urban area or not? And so we could use what we call the dummy variable, where all it does is just, again, takes on a value of 1 or 0 to represent whether the college is in an urban town or not, an urban area or not. Certain types of data that you can collect, depending on the equation that you're specifying. One type is a cross-sectional data, cross-sectional regression, where you're looking at data at a given point in time across maybe different geographic areas. So if we say, I'm going to look at the mean household income in each city in 2000. And so what your data is, again, if you're thinking of kind of an Excel spreadsheet, you have income as the header of your column, and then as you go down the columns, you have different cities for each of your rows. Each row is a different city, and you're entering in incomes for each of those. Maybe if we think of the pizza equation, the y's and the x's are different towns, and it's all in the year 2000, and I've got the quantity of pizza demand in Shreveport in one row, and the demand for pizza in Ruston in another row, and the demand for pizza in Monroe in another row. So all of my rows of data are the different towns that these colleges are located in, and the pizza demand in those individual towns. But it's all for the same year. It's all for the year 2000. Another type of equation you might estimate is a time series equation, where your geography probably stays relatively constant, but the time changes. So instead of thinking about the pizza demand in Shreveport and Ruston and Monroe for the year 2000, we say, I'm just going to focus on Shreveport, but I'm going to include more years. So in this case, the rows might be the demand for pizza in 1950, and the demand for pizza in 1951 as another row, the demand for pizza in 1952 as another row. So each of your rows is a different year, and that's another way you can estimate data using a time series method. There are other kinds of econometric methods that you can use. Okay, what you would think would be the most important part is actually the fastest, actually running the regression. You've determined which variables you think are important. You've come up with some guesses as to the signs that you expect. You've specified your equation. You've collected your data. All of that stuff probably takes you several days or months maybe. And now that you all have it in an Excel spreadsheet, you're going to run OLS, which takes maybe a tenth of a second. So it's very fast. But this is the main thing that you've been working up to. So it's kind of anticlimactic that it takes so fast. And there's no sounds or anything. You don't get a whiz bang or fireworks after you've done your regression. But this is all what you've been leading up to. So you actually run OLS, you run a regression in Excel. You might use other packages like SAS or SPSS, or I think on the Moodle page I also linked to Gretel, which is an open source free econometrics package, which is actually pretty powerful. And so you run your regression, and here's our pizza demand regression that I pulled from the book. And here's the results that I got. So the results for the coefficient was 26.67. In the results, you might see it as, not the coefficient, the constant or the intercept term. You might see it listed. They're always going to list the table of results. And so for the intercept, it might label it as intercept or constant, something like that. 26.67. And then you'll see your other x variables there. And I got a coefficient for my x1 variable as negative 0.088, coefficient for my x2 variable as 0.138, etc. I actually don't have the t-stats in this one, at least on this screen. Got an r squared of 0.717, adjusted r squared of 0.67. Again, since I tend to look at adjusted r squareds when I have multiple x variables, I would tend to rely on that. So what this tells me is that the variables that I've picked explain about 67% of the variation in pizza demand. So it's a pretty good job. You know, about a third of the variation in pizza demand is unexplained, but since this is cross-sectional data, it actually does a pretty decent job. Usually, a rule of thumb that I picked up from undergrad, I guess, is if you're using cross-sectional data, if you get an r-squared it's about 0.3, then you've done a decent enough job. I mean, you've explained 30% of the variation in your y variable. Again, here all I have is 4 x variables, so there's lots of other factors that are going to be important, but if I've managed to explain at least 30% just with the variables that I have, that's a pretty decent job. But here it's all the way up to 67% that I've been able to explain. Here are the results, but I need to figure out, what does this mean? What do these coefficients mean? What does the negative 0.088 mean on the x1 variable? So you have to interpret the results that you get, interpret the coefficients. x1 was the price, and y was the demand for pizza. So what does this tell me? Well, it tells me that if I were to increase my x1 variable by 1 unit, and I can't remember if the price was in terms of dollars or cents, let's just say that it's dollars for now. If I increase the price by $1, then the effect on y is that y is going to decrease by 0.088 units, whatever the units of pizza demand was. I don't know if it was the number of slices. So I see at least that there's a negative relationship here, but again I also see the magnitude of that relationship. If I increase x1 by 1 unit, then y decreases by 0.088 units. So understanding what the coefficients mean is important. Figuring out, did you get your expected signs? And that might not happen. Sometimes you might get a sign that you don't expect. I expected the price variable to be negative. I expected the tuition variable to be positive, and it was. We had the x3 was the can of Coke, and I'll leave that to you to figure out whether you expected that to be positive or negative. You can think about that for a second. And the x4 variable was our urban variable. I think x4 took on a value of 1 if we're in an urban area and 0 if not. And my hypothesis that I kind of sketched out on a previous slide was that, well, if you're in an urban area, there's probably a lot of other options for you to eat at other than a pizza place. So I would probably expect that in an urban area, the demand for just pizza would probably be less because there's a lot of other options out there. And I see here that my x4 coefficient is negative, so I kind of expected that. Just another note here about thinking about these coefficients in terms of partial derivatives is going to be helpful for later. After looking at the coefficients themselves, the size of them, the magnitude, whether you got the correct sign or not, you want to look at those other test statistics to figure out how good of a job your regression did. And so you want to look at what we call the goodness of fit, how well the data fits, how well the estimates fit the underlying data. The first thing you might see is the r-squared or the adjusted r-squared, and you also want to look at the r-squared is for the model as a whole, all of the variables that you've picked as a whole. And you also want to look at the individual variable p-values, whether the individual variables are significant. So again, the r-squared helps us to answer this question: how much variation in pizza demand is explained by the variables that we've chosen? And we said the adjusted r-squared was about 0.67, so we can say, well, about 67% of the variation in pizza demand is explained by these variables that we picked. And then we want to look at our p-values, t-statistics if you want, because again, I know that the computer is telling me that the relationship between price and quantity demanded is this negative 0.088, But I want to know if that's statistically significant or not. So then I want to look at the p-value. If I get a p-value that is below 0.1, then I can say, okay, there's less than a 10% chance that the relationship between price and demand for pizza is insignificant. So I have a 90% chance that this estimate of negative 0.088 is true, or is close to being true, that there is a relationship between price and quantity demand. Just to finish up with a little bit of another summary of my summary, the steps that you'll go through. First, you want to specify the formula that you want. Which y variable are you actually going to use? What are the x variables that you think are important? If you're doing your regression in Excel, you have to be careful. Every time you run a regression, you have to make sure all of your x columns are next to each other. You might have a row of different x variables that you might think are as important, and you might have independent variables in your B column, in your C column, and then another variable in your F column that you want to use in your regression. Well, you can't run your regression with your independent variables being in the B, C, and F column. You're going to have to copy and paste or cut and paste that F variable into D so that they're all right next to each other. It's kind of weird, kind of annoying, but Excel does that. Okay, step 2, you want to make sure you form some hypotheses about the expected signs and maybe even the magnitude of the coefficients that you're estimating. You collect the data. I guess I didn't include that. You want to make sure you actually collect the data that you have. You run your regression in step 3. Again, that happens very quickly. You interpret your results. What does your R-squared look like? Did you do a decent job of explaining the variation in your Y variable? Are your individual coefficients significant? Sometimes they may not be. Sometimes you may get a sign that you didn't expect. So I thought that the relationship was going to be positive, but it ended up being negative. You can kind of maybe fudge it a little bit. If the coefficient is insignificant, then you can say, well, even though I got an unexpected sign, the estimate of the coefficient is insignificant. So you don't, basically the real value of that coefficient is 0. So even though the computer estimated it to be negative and I didn't expect that, the reality is that it's probably close to 0. So you can kind of discard that unexpected coefficient result. But again, it's important to think about, are the signs you got, are they expected? Did you get the magnitudes that you expected also? And of course, you might get results that didn't make you too happy. You might get results you didn't expect. So there might be an error in the data, actually. Maybe there's a coding error. When I was doing my dissertation, there was an error in the consumer price index that threw everything off. And when I finally corrected that, you had values of the CPI that was 120, 121.4, 123, and then it jumped to like 270 just for 1 month. And then it went back to 124, 125.3. So just that 1 month where it was way off, and it threw my results off completely. So once I found that and fixed it, it changed everything, and my dissertation advisor got mad at me because it changed all of our results. Anyway, so there may just be an error in the data that you can fix relatively easily. You might also think about getting a different sample. So you might have gotten data for a few towns in Louisiana for your pizza demand, and you got certain results. You might also think about, well, let me look at the same kind of variables, but I'll use data from Texas, or I'll use data from Arkansas, or something like that, and see if you got results that back up your Louisiana results. Or maybe the Louisiana results were just kind of different, and if you use other states, you might get results that are more consistent with what you thought. Were the expectations you made, were the hypotheses you made based on sound logic? You might have not had expectations that were reasonable. There may be weird things happening if your variables are related somewhat. You may get strange results if the y variable and the x1 variable are defined really similarly. You might think about, well, I'm going to run a regression to try to predict people's height in inches. That's my y variable, their height in inches. And one of the x variables I want to include is their height in centimeters. Well, that's kind of weird because you're explaining basically the same variable on both sides. You're trying to explain their height in inches based on their height in centimeters. Well, there's going to be a kind of a one-to-one relationship there. And so the regression is going to not really know exactly what's going on. It might also be weird if you said, well, I'm going to think about predicting the weight of people as my y variable based on their height in inches and their height in centimeters. So I have my weight as a y variable and height in inches as an x1, height in centimeters as an x2. Well, you're basically measuring height for both of those. And the computer is going to say, well, I don't really know, is x1 more important than x2? It's not going to know how to attribute the significance of height or how to distinguish it between height in inches versus height in centimeters. So you may end up seeing that the r squared is fairly high, if you're measuring weight based on height in inches, height in centimeters, your R-squared might be pretty high, but the individual coefficients, x1 and x2, might show up as being insignificant, and that would be, you'd be like, what's going on here? How can the R-squared be good and both variables be insignificant? Well, it's because x1 and x2 are basically measuring the same thing, and the computer's not able to sort of disentangle those two effects. So this is how you run regressions, and we'll actually use this quite a bit later to come up with, I'll give you data and I'll ask you to run a regression to give me an equation for total revenue curves, total cost curves, that sort of thing.